Hi everyone, I am Davide Conficconi, a third-year PhD student in Information Technology at Politecnico di Milano, and today I have the pleasure to present you our work, a framework for customizable FPGA-based image registration accelerators. Imagine that a physician has a surgery through the aid of a robot, or more in general, a machine, and that it needs to compare pre-operatory images with the current ones. More specifically, these images could present different resolutions and misalignments that the physician would expect to be resolved and realigned. And this realignment process is called image registration. It is a widely spread pre-processing mechanism that it is not only for biomedical imaging, but also for computer vision and target recognition. Currently, in the state of the art, there are solutions that rely on general purpose processor, but they are mostly closed source with good performance, or open source with several functionalities, but loosely performant and power efficient. Considering GPUs, we find many open source high performance implementation. However, they rely on the acceleration of a small portion of the overall process or on dataset specific optimizations that avoid the generalization of these solutions. And finally, GPUs are known to be power hungry devices. Finally, in literature, we find FPGA-based implementation that are all closed source with incomplete details or that have been only simulated, hindering their usage in this field. And for these reasons, what we propose is an open source hardware-software framework for design and synthesis automation, an highly customizable FPGA-based accelerator for the mutual information calculation, and its Python APIs for a transparent usage. The support for the exploration of different design parameters to tailor the architecture to use case requirements. The whole framework is open source on GitHub and available through the DOI in this slide. But before going into the details of our proposed architecture, I will introduce you some background concepts behind image registration. This process consists of finding a geometric transformation to realign images. And within this context, image registration methodologies can be grouped into mono and multimodal. In the first case, images are taken from different points of view, but from the same sensors. While the second exploits different types of sensors. And moreover, we can find in literature approach based on features detected from physicians or approaches based on the intensity of the images, and so without any assumption on the data. Generally, the multimodal workflow to register two images is an optimization procedure that's starting with the initial condition estimation, and it is followed by a transformation of the floating image, whose goodness is evaluated through a similarity metric. This value is used by the optimizer to determine whether convergence is reached or not. If yes, the process ends. Otherwise, we will update the parameters and repeat the loop until convergence. Considering the different blocks of this heuristic process, both the literature and our analysis have shown how the transformation and the computation of the similarity metric are the main bottleneck of image registration. And based on these considerations, in this work, we considered a multimodal workflow exploiting mutual information as similarity block. We designed a customizable and optimized architecture for the mutual information calculation. Being the core of our work, I will introduce the basic concepts behind mutual information. It measures the statistical dependence between two random variables through the entropy's computation, highlighted here in green in the slide. In turn, entropy is defined as the measure of uncertainty of a random variable, and it requires the computation of probability distribution of our variables. Based on this formula, the probabilities are computed starting from the histograms of the images that represent the intensity distributions of each image. So from a high-level point of view, our Moodle Information Accelerator has two macro stages, the histograms and the entropies. All these computations within our accelerator are pipelined and exploit a data flow execution model. We will start by analyzing more in detail our architecture and highlighting the customizable parameter of each stage. Moreover, we will estimate their coarse-grained latency. Let's now consider our first macro stage, the histogram one. At first, we retrieve both the images from the off-chip memory, and here we pack the input pixels in a single packet by a factor of packing HPE pixels. Moreover, when registering two images, the reference one stays the same through the entire optimization phase. Hence, we may consider to cache it locally on the on-chip memories if we can. We consider as input data images of ESS pixels, each of which is ABW bits wide. In this way, our first stage has to unpack the pixels with an overall latency of ESS over HPE. Moving ahead, stage 2 and 3 computes the joint histogram. We adopt here a MapReduce approach, where we map the joint histogram computation on a number of HPE parallel processing elements. We optimize each of these processing elements to be hazard-free, and the cost of our map requires us to store a joint histogram of size HS times HS that depends on the pixels bandwidth of the input images. Moreover, at the end of both stage 2 and 3, we pack the output into a stream by a factor of EPE, and this will be useful later. Stage 2 reports a coarse-grained latency equal to reading the unpacked image streams plus the time of packing the joint histogram that is overlapped with the processing. Instead, stage 3 has to read the input and reduce it, and finally pack it out. Stage 4 replicates the joint histogram 3 times, and then stage 5 exploits the fact that the separate histogram of the images may be derived from the joint one by columns or rows reduction, as shown on the right-hand side of the slide. And also here we step back the output stream. Each of the stages needs to read the stream, perform the operation, and output the packet stream in an overlapped fashion. Then we enter in the entropies macro stage, where, thanks to our previous spec, we can split our data streams and apply a MapReduce by a factor of EPE for the entropy computation. It is important to notice that at this point, we can choose between floating or fixed point computation for the entropies. And here, stage 6 and 7 have a variable latency, depending whether they are computing the joint entropy or single ones. And this is caused by input streams that are of different sizes. While stage 8 is dominated by the reduction of floating point operations. Finally, we combine all the entropies to compute the final Moodle information value and apply the formula in the slide. This is the overall representation of our Moodle Information Accelerator. We can employ it in a single core design, or if we have at disposal a system with many off-chip memories, we can bind each core to a bank either physically or logically, obtaining a multi-core architecture. So, through the description of the accelerator, I presented several customization parameters that are exposed to the user thanks to our framework. But going into the details, we should keep in mind that HPE and EPE, that are the MapReduce factors, have a high impact on both the execution time and resources. And this is shown in this chart, where the latency of the architecture is particularly affected by the scaling of these two parameters. Here we can see how increasing them and fixing all the others, the overall latency decreases nearly exponentially. Moreover, our framework exposed to the user the chance to target different Xilinx FPGA technologies. On top of which, thanks to the drivers and operating system, mainly here coming from the PINC framework, we built high-level APIs that ease the accelerator usage, making it transparent to the final user, that can build her own application layer without explicitly managing the underlying hardware. Moving to the setup, we employ 4 different boards: a PINC-Z2, an Ultra 96, a ZCU104, and an Alveo U200. We compare against Matlab image processing toolbox that employs Moodle Information and 1+1 as the optimizer. On the other hand, we employ our accelerator combined with 2 different optimizers, 1+1 and powers. As dataset, we employ a stack of 247 medical images for our multimodal use case. On the following results chart, we will employ an acronym that is defined as follows. The first number represents the number of cores. Then we may find if the architecture employs caching or not, which kind of data type we employ for our entropies, how many processing elements for the joint histogram, and how many for the entropies. Say that we will mainly analyze the Ultra 96 and the Alveo U200 as representative results of 2 different device classes. In this chart, the utilization of Ultra 96 shows that our accelerator is mostly demanding for VRAM and DSPs. Moreover, we analyze the behavior of a single core that scales in the number of processing elements for the histogram and for the entropies. We can see that increasing them reduces the single Moodle Information execution time, as we expected from our estimation result. Instead, we can see that on an Alveo U200 that has much more resources than an Ultra 96, we were able to scale to multi-core architectures. In addition, we can see how VRAMs become the main limiting factor when considering multi-core designs with caching. We then analyze the execution times of the Ultra 96 with both Powell and 1+1 optimizers. And here we can see that comparing to Matlab with the same optimizer, we achieve a top speedup of 2.66x against an Intel i5 and 1.49x against Xeon. Moving to the Alveo, we consider now only 2 Matlab implementation on the Xeon. One as before, without the parallel toolbox, and the other with the toolbox enabled, that exploits further the available resources. Here we can see that Powell, the slowest approach, is in line with Matlab with the parallel toolbox, while our 1+1 achieves better result with a top of 2.86x and 8.62x with and without the toolbox respectively. Moving to the comparison with the state of the art, we employ an existing metric that represents the time over the number of megavoxels per number of optimizer iterations. This metric was previously proposed, trying to introduce a general evaluation metric for all the possible different approaches. We also enrich this metric by computing the power efficiency, counting as performance over kilowatts. Considering FPGA-based works, our 1+1 implementation outperforms all the others, even when comparing the same technologies, while Powell method is in line with literature results. Unfortunately, we cannot compare the power efficiency given the lack of data of related work. From now on, we keep, for sake of simplicity, only Ultra 96 and Alveo results. We compare against GPU-based works, and here the most competitive work exploits some dataset specific features, while we did not bias our optimization procedures. However, 1+1 based is still better. Considering instead power efficiency, we can see that our FPGA-based approach achieves far better results. Moving to the approaches based on CPUs, we can see that simple ITK that provides several possible combinations achieves lower performance. On the other hand, Matlab, with the parallel toolbox enabled, achieves performance almost in line with our top Alveo, while we deliver power efficiency that are notably higher. Concluding the results evaluation, we compare the accuracy of our hardware-based image registration against the Matlab one. Starting from the gold standard on the left-hand side, we show in yellow the registration results, and in green the gold standard position for each of the three methods. As we can see, our hardware-based solutions employing Powell achieves the highest result. In conclusion, with this work, we presented an open-source framework for design and synthesis of a highly customizable and optimized FPGA-based accelerator. We show a 2.86x on an optimized state-of-the-art Matlab implementation, showing outstanding power efficiency results. As future work, we plan to validate the architecture on different fields and explore different and new degree of customization. This is all from me. Thank you for your attention. Feel free to drop us an email.